Welcome back to the part 2 of the fractional knapsack algorithm. I written the problem, the general setup of it. In this video, I'll be a little bit more formal, less examples. Okay, so you saw the examples in part 1, and let's start to try to understand this problem and give it sort of an idea of a proof, a more formal interpretation and explanation of how this greedy, or why the greedy algorithm is working, and first of all how, and then the why. Okay, so we have the target function, the sum of the values. We can choose, we have n items to choose from. We can choose a fraction of them or all of them. So xi, our choice variables, can be between 0 and 1, can be 0, can be 1, anything in between. But we cannot carry more than a certain weight. Each item has its own weight, this wi, and this is capital W. Again, if we are economists, we think about cost, and this is our budget constraint and so on. But let's stick to the story behind this algorithm, or this problem. And again, without loss of generality, let's assume, okay, we saw that we computed the density. So let's assume now, for sake of the argument, that V1 over W1, okay, the density of the first item, is strictly bigger than V2 over W2, and we will continue, okay, like that, and that's bigger than Vn Wn. If it's not like that, we will sort it like that, name those items 1, 2, 3 until n, from the most dense one to the less dense one in terms of value. Okay, so we can write the density rho I is Vi over Wi. Okay, and rho I is bigger than rho I plus 1 in this setup. Okay, and it, again, without loss of generality. Okay, so here is how the algorithm is working. Okay, the greedy algorithm. First of all, let's define quantity R, which is how much weight remains to be put inside the sack. In the beginning, it's empty, and R is set to be equal to W. We are still have nothing in, so the total amount that we can carry is still available to be filled. Okay, so R is equal to 1. Now we, at each step, okay, R will be what remains to fill. In each step I, okay, so we call this step 0. Step 0, okay. In step I, okay, we will say, okay, if R remains, let's compute, okay, or let's look at the weight of the now item. Okay, so we already put I minus 1, from 1 to I minus 1 inside our pack. So we are at I. Should we add it to the sack? Should we not, or part of it? So we are asking, is Wi less than or equal to, okay, less or equal to than R? Okay, if the answer is yes, we will put that item I inside our backpack, and we will set R, okay, equal to R minus Wi. Okay, there now less remains to be filled in what we can take. Okay, and then we will increase the counter. Okay, so if this is true, then put it inside, then set this. Okay, what if the answer is no? Okay, so if not, if Wi is bigger than R. Okay, So the question is, how much is okay? So R, we assume that it is still positive. It's not 0, because if it was 0, we would stop. So R, there is something more to be put, some more space to be used inside our knapsack. So if W is bigger than R, what we will do, we will take how much remains, okay, and we'll take just part of the weight there. So we will take, okay, so here when I set, if this is true, okay, also one thing that we have to do is xi, set xi equal to 1, okay. It means that we are taking item I. So if not, okay, then we set xi equal to, and we'll take only fraction, okay, since R is less than, okay, so it's R over Wi, okay, okay, and we will set R equal to 0, done, okay, we have now no room left, okay, so this is, all of these are in step, okay, these two questions. If this is true, okay, done, and then set I equal to I plus 1, and go back here. Okay, and then if this is R equal to 0 here, then stop. Okay, and anyway, it has to be written that if we could put everything in the back, and still there would be, it's not full, we will stop when I is equal to, either R is equal to 0 or I equal to n, no more items to choose from. Okay, so stop if R is equal to 0 or I equal to n. Okay, otherwise we will go back to step I. Okay, so that's the greedy algorithm. We are very greedy at the beginning. We take all the most dense material, put it in our backpack, and then we go down the list until we have to stop or we are run out of items. Okay, so this is the description of the algorithm. Okay, and in a more formal way, okay, formal solution. Okay, we will set xi equal to 1. Okay, for I less than some index k, okay, such that k is the smallest and this is strictly less than k, okay, so it's the smallest index or okay, or natural number index for which, okay, we ran out of capacity, okay, so for which the W minus sigma I goes from 1 to k, Wi is less or equal than 0. Okay, so we already used up to including k, okay, we cannot take, either we are done in capacity at item k or we ran out of capacity. Okay, so for all of them strictly less than k, it's equal to 1. For xk, okay, which will be equal to, okay, what's left? So what's left will be this W minus sigma. I goes from 1 to k minus 1, okay, up to k until now, Wi. Okay, so that's the R that we wrote there, divided by Wk, okay, and we will set xi equal to 0 for all I bigger than k. Okay, so for I strictly less than k, it's equal to 1. For I equal to k, xk is equal to this value. Okay, that might be 0. Okay, if this minus this is exactly 0, then it's 0. But anyway, anything above k, this minimal smallest index, 0, we ran out of room in what we can carry. Okay, so that's the formal solution that we have here. Now, there are two things that I want to say before finishing here. We use strict inequalities. What if there are ties? Okay, so what if okay, ties? What do we do? Okay, if it's V3 over W3 for some reason is equal to, or it happens that they have the same density. What do we do here? Okay, so it's not very complicated to understand that if K, okay, is equal to 3, okay, then we have no problem with it. It doesn't matter if we name 3, 3, and 4, 4. We switch the names and 4 becomes 3 and 3 becomes 4. It doesn't matter. It's the same. We only care about maximizing the value that we will take with us. So it doesn't matter if we stop there. If that equality happens above where we set 0, then we will set both of them 0. It doesn't matter. If that equality happens lower, strictly lower than this k, then again, it doesn't matter. We will take both of them. Okay, whether we decided to take 3 first and then 4, or 4 first and then 3, it doesn't matter. It's only naming of this item, so ties are not a problem. Another thing that I want to mention here is that this problem, okay, and I will leave it to you to think about it, can be written as using a Kanpsack condition. So that means that we will have a lambda minus these constraints, and we will compute basically what we call as economists the shadow prices of every item. And the solution following the Kanpsack theorem and the technique will basically show us also another way to prove that the greedy algorithm is working. And by the way, the inside the proof, it's longer. We can show that if we follow this and then we say, okay, what if we stop at 3 and suddenly we make an exchange? We take number 6 and we exchange between them. Will we be better off? No, of course not. Okay, because the density of 6, the way we order them, is lower than the 3 that we chose, and we cannot improve upon working in this way. Okay. Another thing that is worth mentioning is, okay, so what's the computational burden here? The first step is, and I assume it because that's math, but you will have to order the items like that, and the computational complexity of ordering is O n log n. Okay. And after doing that, going over this loop of computing each time what remains for us to take is O of n. Okay, so overall, both of them, since this is bigger, it's O n log n. Okay, so we could write it like that, but it's this order of magnitude of the algorithm. Not too bad. Okay. Again, next time, in the next videos, I will see examples that are a lot more connected to partial identification. How does all of that relate to partial identification that I talked about in other videos? We will see that later on. Again, thank you for watching.